So the title on Q was meant as a bit of a joke, and I wrote to Vitali, this is a joke, maybe you want something more serious. But he took it, but then he added the more serious alternative as a footnote, so now it got a little longer. What I want to talk about is sort of suggested by the following amazing coincidence, that this symbol, which is not a 9 but a Q, occurs in at least 4 different places in mathematics, so far as I know, quite independently. On the one hand, you have, let's see if I can now think of them, of course. You have, well, Q series, which is something that comes from combinatorics. So a typical example of that, for instance, is the, wait, how does this work? I should have stripped these before. The Q binomial coefficient, for instance, you start with the usual binomial coefficient, n factorial over k factorial, n minus k factorial, and you replace n factorial by the symbol, often written q in brackets sub n, which is the product 1 minus q squared up to 1 minus q to the k. And then you perceive, this was already done by Gauss, so it's very classical, that this thing satisfies exact analogs, well, or generalizations, in fact, of the Pascal triangle identity, which it would be if q were equal to 1, and of the q binomial theorem. If instead of taking 1 minus z, I've chosen z instead of minus z just for convenience, if you take 1 minus z to the nth, in the usual case when q is 1, and replace it by the product 1 minus z, 1 minus qz, etc., then the expansion of that is minus z to the k, and then the usual binomial coefficient becomes this new q binomial coefficient times the power of q. So this has developed into a huge industry, very, very beautiful, Q series, Q combinatorics, in which things like hypergeometric functions are systematically replaced by their Q analogs. Every factorial inside becomes a Q factorial. The definition of a hypergeometric function, which is that the ratio of the nth term to the n minus first term is a rational function of n, gets replaced by a rational function of q and q to the n. And then there's this beautiful field of combinatorics, and everybody uses the letter q who does that. Now, another field which we've been hearing a lot about is modular forms, very dear to my heart. And that's been the theme of this afternoon and of the discussion that follows. One of the themes of my talk will be, in certain situations, the unreasonable ineffectiveness of modular forms, or at least the effectiveness sometimes of other things. Now, there's a third one, which here you might say, maybe if we now use Q, after all, there's still Q series. People write things here which, when you multiply them out, typically are power series expansions in Q, and the same is true here. But another Q, which no one will accuse anyone of having been the same, is everybody uses Q for finite fields whose order is not necessarily prime, but a prime power, and that's obviously simply because Q comes after P in the Latin alphabet, and so is visibly independent. And the fourth, of course, is the Q of quantum theory, which I also think was not named quantum theory because this Q had been already used for 50 years. So the remarkable thing is that all of these are connected. The connection with the FQ I'm not going to say very much about. Let me just say a word, but there's much more to be said. Actually, Maxim Kontsevich has some very interesting ideas on this, but again, there's a real literature. But if you take, for instance, the number of points in the Grassmannian of k-planes in n space, I hope I got it right, over FQ, then you get exactly this binomial coefficient of Gauss. So there is a direct connection, and it's a little strange, because after all, the first Q is a formal variable. The Q of Q series is a formal variable. You don't care what it is as a number. The Q here is a complex number which is less than 1. The Q here is, well, it's 2, 3, 4, 5, 7, 8, 9, 11. I mean, it's not less than 1, and it's some very specific integers. And the Q of quantum theory, well, the Q of quantum theory doesn't really exist. It's a formal variable again, which comes up when you quantize certain algebraic theories. And typically, however, you can assign real values, complex values to it, and specialize the theory to a complex value, and then things will be especially interesting when Q is a root of unity. So I'll just put especially at Q of root of unity, although in many parts of the theory, these are exactly, I'll push this in case you can't see, these are exactly the ones you don't want. Sometimes the theory breaks down there, sometimes it's most interesting there. Sorry?
What is a Q in quantum theory?
Well, I'm just saying, for the moment, it's just the first letter. And you specialize it. Now you'd like it to be a root of unity. Come on. If you don't find out, then I've something has gone wrong with the talk. All right, so let me give you the very first example. So the Q, I mean, there are things floating around to which huge contributions have been made by many people in the audience, and I won't attempt to mention them because I'll leave out the right ones. But there's, for instance, SL2Q and so on. There's a theory of quantum groups. There are also quantum invariants in topology, which I will get to. And there's also the relation, which was already mentioned by Kahn with his non-commutative torus. And that, in fact, connects up directly with this, but I won't be able to talk about that, partly because I don't understand it yet, partly for time. But there's a true connection. And here, on the most primitive level, you can see the connection like this. If you take that funny binomial, here I made a kind of an artificial generalization of the usual binomial theorem. The usual binomial theorem is x plus y to the n. And I put 1 minus e to the n and then put in funny powers of q. But the natural generalization is x plus y to the n as it stands is the sum n over k x to the k y to the n minus k if yx equals qxy. And again, special things happen if q is a root of unity, and that you can certainly see in this baby example, because if q is a root of unity, then this thing, which is a polynomial, may have zeros, right? I mean, it's trivial by this inductive property that the q binomial coefficient is a polynomial, so there's no poles, and obviously zeros can only be at roots of unity, and then special things will happen. So the general theme here is, first of all, that one should eventually think non-commutatively. That's the theme of the whole 21st century, and even bits of this century, ever since Kahn came into the picture, and perhaps even before. But I won't talk about that. This was just a hint. So what will come into my story is this specialization to roots of unity. So this was kind of to get things moving. Now let me go back to q-identities and to modular forms. And let me start with some of the very most classical q-identities that I know, and also some of the most beautiful. So first, I'll take 3 from Euler's I'll say it in English, Introduction to Infinitesimal Analysis, chapter 16. Chapter 16 is already in English. And here are 3 identities chosen from many, many, which Euler proved, and you can find in many books, for instance in Euler, but also in Hardy and Wright. And each of these things has a combinatorial interpretation. For instance, the first one, the product 1 plus q to the m, counts the number of partitions of a number into I'll probably not take a good example. It counts the number of partitions of a number into parts of different sizes. And now if you have such a thing, this probably wasn't a good example, and you cut off, I'm bound not to get it right, since the parts are of different sizes, if I start at the beginning, at the bottom, I can cut off at least 1, 2, 3, and 4 elements, and then the bits that are left added onto this part, which is m times m plus 1 over 2, is a different way of counting the partition. And if you write that out, you get the first identity. And similarly, the other 2 have combinatorial interpretations. The third one, of course, is the famous expansion of the eta function. So these identities, Euler proved by purely combinatorial means. They're true, as it happens, as convergence series, but they're actually to be thought of as formal power series identities. 2 other identities. One is the Jacobi triple product from his book on elliptic functions, which most people have seen, which again says that a product of something has an expansion q to the n squared with various modifications. And a yet much more exciting identity is the so-called Rhodes-Ramanujan identity, discovered independently but 20 years apart, 25 years practically by Rhodes and Ramanujan, so they both get credit. And that says that this sum, which looks very similar to the sums I should have written on the left, the sums there are q to the n squared plus n over 2 over 1 minus q squared over 1 minus q to the n. And this look almost identical, only the numerator has changed slightly to q to the n squared. But now the product has a very bizarre 5. Oh, I missed the main point. This 4 isn't 4, it's a 5. N is congruent to 1 or 4 mod 5. So this is a product over certain numbers. Actually, since it's so pretty, while I'm talking for the next 2 minutes, I'll write the full Rhodes-Ramanujan identities on the board. I assume everyone has seen them, but if you haven't, you should see something nice from the last century before we move into the next one. So, actually from the century before last, I guess, turn of the century. But these are probably the most beautiful specific identities in the whole mathematics literature. So the first one, G of Q, is the one I just wrote down, and this identity is the one I just told you, and there's a companion, H, with n squared plus n, where n is congruent to 2 or 3 mod 5 instead of 1 or 4. And then the quotient of those 2 you can also write using the triple product of Jacobi as a quotient of two highly lacunary things, which are theta series, with just a tiny number of terms, and then finally there's Ramanujan's beautiful continued fraction. So you get the remarkable result that this is equal to the product 1 minus q to the n to the power minus n over 5, n from 1 to infinity, which is somehow a glorious identity, but of course not what I'm talking about. Now, until recently, the explanation of these identities, as I said, there are combinatorial proofs. You can just sit down and prove them, as Euler did, or maybe he didn't sit down. No, Euler proved them. This one, the last one, he conjectured, and it took him 15 years, so he found a proof, but he proved it. He first computed 50 coefficients by hand. Another example of blood, sweat, and tears that we've been hearing about. He didn't conjecture at random, and in his case, he didn't just conjecture, he did prove, and I believe the other two also. I'm not entirely sure, but the last one I know he proved, because it took him many, many years until he was able to prove that only those coefficients occur. Now, what I was saying is that the usual explanation of these things, and it's certainly correct, is that the reason, the deep reason why such identities exist in such profusion is the theory of modular forms. The fact that there are certain functions which have the special and wonderful property of being modular. So, well, one of them is the function eta of z. Well, we already had one, but I'm too short to write it. But Peter already wrote it. It's a very unfair blackboard. They could have a little step here. Okay, so he already gave the example of the function. Well, he wrote delta of q, and I didn't say anything, but one might have. Delta of z is the function q times the product n from 1 to infinity, 1 minus q to the n to the 24, where q, this is kind of universal in this field, e to the 2 pi I z. Everyone uses q. Some people, including me, usually use tau instead of z, but q is sacred because otherwise my joke wouldn't work. Okay, eta of z is the same thing, but you take the 24th root. So in a sense, it's much more natural. And in fact, if you remember the notation, bracket qn, which I introduced in the very first slide, this one, for my q binomial coefficient, then this would just be q infinity up to this strange, well, it's not strange from the point of view of higher mathematics, like Kac-Moody algebras and so on, but from this point of view, it's a little odd, and certainly Euler didn't realize that his series became much more natural if you included a function, q to the 1/24th, before putting this infinite product. But the point is that this thing is modular. Well, Peter already gave us the equation saying that delta was modular of weight 12, and since I've taken the 24th root, this thing is modular of weight 1/2, and we've already seen modular forms of half-integral weight in Hendrik's lecture before. Okay, now, why does that prove something like this? Well, on the one hand, so this is the left-hand side of this identity, except I've multiplied by q to the 1/24th. The right-hand side also becomes much better if you multiply by q to the 1/24th. Namely, if you take this expression, sum minus 1 to the n q to the 3n squared plus n over 2, multiplied by q to the 1/24th, then this is what you learn in high school about completing the square. This thing now becomes simply a square divided by 24. Now we all can restrict to n positive because n and minus n have the same square anyway. And then it turns out that the coefficient you have to put here is a character, one of those quadratic characters that occurred in both previous lectures. And it's the character 12 over n, which, if you don't know it, 12 over n is 1 if n is congruent to plus or minus 1. Mod 12 minus 1 if it's plus or minus 5, mod 12, and 0 otherwise. So that's an equivalent way of writing this identity. But now the point is that this thing is immediately a modular form because it's a theta series, q to the power a quadratic form. The theta series were also mentioned in maybe both of the previous lectures, but certainly in Ivanitz's. So this is a theta series, and therefore it's a modular form of weight 1/2. This is a modular form of weight 1/2, it's already mentioned by Peter. And if you compare those two facts, it's known that if any two modular forms, which look like they're the same, are known to be modular, then they are the same. And when I say they look to be the same, you just compute enough coefficients, and you know how many enough is. So if you conjecture an identity, and you can prove that both sides are modular, then you're finished. So this is the great power of modular forms. But somehow what I want to say today is that there's more, that there's an aspect to what's going on with modular forms and what's going on with this Q, which has a little more of the flavor of these other points of view. Now, to my great regret, I will not be able to tell you anything at all about what happens when you take a modular form and take this Q to be a prime power. I would really dearly love to, but I can't. So what I will talk about is, to some extent, formal Q-series, and the way that formal Q-series may have very good properties, beautiful properties, for the same type of reason as if they were multiforms, but even though they aren't multiforms. This was discovered by Ramanujan in his last letter to Hardy in January 1920. I'll put up the slide now and then maybe come back to it later. I don't want to overwhelm you with formulas, or rather I do, but I don't want to yet. In this famous last letter, Ramanujan introduced, I can't say he defined because he didn't define, but he introduced a class of functions which he called the Mach theta functions. And he gave 17 examples, 4 which he said were of third order, 10 were of fifth order, 3 were of seventh order. There was no explanation at all what a Mach theta function was, why these were examples of it, what special property they had, why they had orders 3, 5, and 7, and so on. It was extremely mysterious. He gave 1 or 2 hints, and then, of course, he died, and it took the last identity he wrote down was only proved about 10 years ago. So here's one of the identities. I'm just showing it to you now for the moment. This is one of order 3, and I'll come back to it. This is not a modular form, and Ramanujan knew it wasn't a modular form. I've put in black brackets minus a 24th. It's just like with Euler's story. Ramanujan, of course, didn't have the q to the 1/24th. He had an integral power series. But even though this thing isn't modular, it's nearly modular. I mean, it behaves very much like a modular form, but only if you include the q to the minus 1/24th. So there's a normalization that he didn't put in. And what he said, and that's completely correct, is that this has the following nearly modular behavior. Again, don't worry about the details. I'm trying to give a flavor, because this is the first occurrence of this idea in the literature, and in fact the last for 70 years, I think, that you should look at modular forms at roots of unity, where they aren't even defined. And this isn't even a modular form, so it was even braver. But what he did is he said, as you tend to an nth root of unity, so let q tend to say to n, not necessarily the standard nth root of unity, any exact nth root of unity, then you write down this product, 1 minus q to the n cubed, so it's over 1 minus q to the 2n squared, so it's really 8 of z cubed over 8 of 2z squared. And of course, you should really put in that factor, which I put in to make it truly modular. Then he said, sorry, I left out not the most important thing, but a very important thing. This is not an equality, but the difference between f of q and this modular form multiplied by plus or minus 1 is bounded. So as you go to a cusp, this modular form at certain cusps, which means just rational points, so as z, I should have called it z, as z goes to a rational point, that means q goes to a root of unity, then for certain roots of unity, this thing blows up exponentially. And then he said that f of q will blow up exactly the same way up to a bounded quantity, except that sometimes it's exactly the same way, sometimes it's the opposite. So specifically what he wrote it in a more complicated notation, is that if the order of q is even, then this sign is minus 1 to the n over 2, where n is that order. If the order is odd, it doesn't matter what you write, because this tends to 0 exponentially fast anyway, and so the whole thing is bounded. So there was this strange behavior that the function looks as if it's trying to be modular. It behaves in exactly the same way as you tend to rational points, or cusps, or roots of unity, depending on your point of view. So it's trying to be modular. It isn't modular, but it's somehow nearly modular, and it's also nearly a theta function because of certain other identities, and he called it a Mach theta function. So later, maybe, if time permits, I'll come back to that. But even if I don't, many of you have heard at least the word Mach theta functions. You will know that they are another example of the phenomenon I'm trying to give some feeling for, and which I don't understand at all, by the way. It's very much a lecture for the future, because I'm just talking about 1 or 2 very, very minor examples that I do know, and which suggest that there's that there's another point of view out there which we haven't yet really exploited. So I'm not at all talking about major research results. The actual results I write down are, in many cases, mine or even of a student, but they're not. The point isn't the results as so much as that this should be a general phenomenon. All right, so the phenomenon, maybe I'll get rid of this thing and use the board, even though I'm too short for it. So the general phenomenon, as I said, is somehow Q-series, which we're going to expand at roots of unity, and modular forms, which we're going to look at roots of unity. Is it actually better with the light? When I sat there, it was better in the dark because it reflected. Do you want the light? I think not.
He wants it.
Sorry?
He wants it.
Ah, I see. It's not the odds and two counts. All right. All right, so let me say then the general idea is that modular forms of whatever sort they may be, or even nearly modular forms like the Mach theta functions, do something, some behavior, something at roots of unity. I mean, I'll indiscriminately use the notation, I'll talk about rational numbers and roots of unity, by which I mean if you're in the upper half plane, which is where z is, and you tend to a root of unity, which is in R, which is the boundary, well, except for the point of infinity, it's the boundary of the upper half plane, then of course q at the same time will tend to e to the 2 pi I alpha, which I'll typically call either zeta or xi, which is a root of unity. So I talk about either roots of unity or rational numbers, depending if I'm thinking in terms of z or q. All right, so the claim is that something interesting happens. Now, this claim you can substantiate on the level of classical modular forms, where it's very simple, but I'll already do it there briefly. Mass forms, which are the automorphic forms, the eigenvalues of the Laplace operator, which played a prominent role in both of the previous lectures, so maybe, although I wasn't going to, I'll say something about that case. And then also in the case of modular forms of half-integral weight, and of Mach theta functions, and those two connect up, and undoubtedly also in higher dimensional analogs, but those I haven't looked at all. So let me start in the classical case. So in the classical case, let me start by the following crazy thing. Some of you know probably at least the existence, or maybe the definition of an arithmetic function of pairs of integers, usually called S of P and Q, which is the Dedekind sum. And now I want to introduce a somewhat more general Dedekind sum, which if I can find my notes. Here we go. So a Dedekind sum, well, they were introduced by Dedekind, as you might think, but actually to explain something Riemann had done. The Dedekind sum, the classical one, is a function of two variables which satisfy certain identities, and the identities are that it's a function of P and Q. It's periodic in P with period Q. So if you fix Q, it's a periodic function of period Q. So if P is congruent to P prime modulo Q, this Q is not that Q, by the way, it's simply an integer, positive integer, then D of PQ is the same. All right, that's the first property. And the second property, well, for the classical Dedekind sum, there's a reciprocity that D of PQ plus D of QP is something, but I want to introduce a different one, which is, that one actually is a little degenerate. For the experts, it's connected with the Eisenstein series E2, and E2 is not even a modular form, and it's certainly not a cusp form, and I prefer a cusp form. So I'm taking a different example. So this is capital D. I would use little d for the usual Dedekind sum. D of PQ minus D of QP is equal to, it's only defined, by the way, for P and Q coprime. And this is equal to, it's not terribly obvious, but the right definition is P to the 10th minus Q to the 10th minus 691 divided by 36 times P squared times Q squared times P squared minus Q squared cubed. Now that's not a very plausible definition of anything at all. But in fact, it's the correct definition of, well, in fact, of D of PQ, to be precise. So let's look how it works. I start D of 1, 1. Well, I'm not sure if it follows, but if it doesn't, I normalize. D of 1, 1 is 1. Now D of 2, 1 is minus 1049. And that's because if I take 2 and 1 in this polynomial, I have 2 to the 10th minus 1 minus 691 over 36 times 4 times 27. So this part is 3. So that's 1023 minus 3 times 691 is 2073, which is minus 1050. And then you add the one that we already had, and you get minus 1049. And you can continue this process, and the point is that it's, although the definition looks ludicrous, it's at least obvious that I get some function, because by the Euclidean algorithm, if I have anything like 5, 3, I just keep reducing the bigger number multiplied with the smaller number. Sorry, I meant 3, 5 here. And here I meant 1, 2. If I wanted, yeah, I should have got the periodicity the other day, so other way, so maybe all the signs are wrong, I'm sorry. This is the smaller number, so this corresponds to 1 mod 2, this is 3 mod 5. But the point is that by reciprocity and periodicity, you just use the Euclidean algorithm. I can replace 3, 5 by 5, 3 using the duality, and then I can reduce 5 mod 3, and then I have D of 2, 3, and then I can interchange them, and I continue to D of 1, 1. So you continue, and you can, I mean, this is just an example, and so on, so you get some numbers. Now, when you do this, that looks complete. Of course, I could have put anything on the right-hand side. I haven't done anything. But now, I do the following. I take this number, which is fairly large, but you can see that it grows roughly like the 10th power, because this is a homogeneous polynomial with degree 10. So it's not unreasonable to look at this thing divided by q to the 10th. And since p and q were co-prime and q was positive, I now can write this. Okay, so this is now a function from Q to Q. But now the remarkable thing is that it's, although this is certainly not obvious from anything, that it extends continuously to a real function. So this rather crazy definition extends. This is actually a continuous function. Now, on the other hand, the periodicity p goes to p plus q means that f of x plus 1 is equal to f of x. And it's also trivial to check that f is an even function if you send p to minus p, because if you define d star of pq to be d of minus pq, it satisfies exactly the same identities, and so by uniqueness, it's the same function. So this is an even periodic function, and therefore, f of x, since it's even and periodic and it has no constant term, believe me, that's why I normalized to have 1 here, it will have the coefficient something times cosine of 2 pi nx. Now, if you compute these somethings numerically, the first one is just some horrible constant, which I have to 30 decimals, but it's just a number. But if you normalize so that the first one is 1, then the nth one is tau of n over n to the 11, tau of n being the coefficient that you saw in the previous lecture, the coefficient of delta. In other words, we start with this very simple function on pairs of integers. We think of it as a function only on q, but then we think of that function q as the limiting values of things in the upper half plane, and we somehow integrate up into the upper half plane, and lo and behold, the multiform comes up, and they all come up this way. I mean, the entire theory of multiforms can be encoded in terms of these functions. This isn't terribly interesting. It's essentially equivalent with the Aither-Shimura-Manin theory of periods, which has been understood for many years. But I wanted to say that even in the classical case, this phenomenon of roots of unity happens and is quite amusing. Now, since we heard a lot about, so let's call this example 1. Example 2 of the phenomenon would be, that's the one I said I hadn't necessarily been planning to give, but since it played a prominent role in both other lectures today, let me do it. So I have a function which is a function from H2, Peter called it, modular SL2Z to C. So it's an SL2Z invariant function. In other words, f of AZ plus B over CC plus D is equal to f of Z. And it's an eigenfunction of the Laplace operator, as we've been seeing. Delta is not y to the minus 2, but y to the plus 2 times this. And so, as we've been hearing, there's a discrete spectrum of this. The eigenvalues are somewhere. I mean, the first few hundred are known to extremely large accuracy, both the eigenvalue s and the coefficients. And such an f, as we were also told in the talk by Vanitz, has an expansion. If I write z as x plus iy, then I can write it in terms of Whittaker functions, which here are simply Bessel functions, as the sum of certain numerical coefficients times a k Bessel function, k minus a half of 2 pi ny. So this is just a consequence, an immediate consequence of the Laplace equation, which is here, which I have to erase because I misjudged the space, e to the 2 pi I nx. So in other words, you expand in terms of these Whittaker or Bessel functions, and you get certain numerical coefficients. Now, how can we understand such a thing? Well, you already heard the answer. We can't. It's totally unknown what the eigenvalues are, what's going on, even for SL2Z, or I might say especially for SL2Z, because for some groups we at least know some of these functions. But there are things you can do, and one of them is a beautiful discovery made by Dieter Meyer a few years ago, and another is a beautiful discovery made by John Lewis also a few years ago, and these two things connect up also in a very beautiful way. And let me just say in a few words what happens. So the question is, which S occur? So we know that there's some discrete set of S's, well, they come in complex conjugate pairs, which correspond to these, which are the eigenvalues, or S times 1 minus S. And the question is, so to speak, how can you recognize for a given S whether it occurs or doesn't? Well, this question was answered in two different ways. One answer is sort of the Selberg zeta function, but it's not very explicit. The other two are also not very explicit, but let me describe them very, very briefly. The Selberg zeta function is a function introduced by Selberg in connection with this trace formula, and it's defined, so gamma is PSL2Z here, it's defined as the product of, I won't write it out, of certain geodesics of something. I mean, you take a product of primitive geodesics and you do something. I don't want to write out the formula, most of you have seen it, but it's known that it has zeros, well, except for some trivial zeros, it has zeros exactly at these spectral parameters, Sj. So somehow, this is, again, it's not an L function, of course, in the sense of the lecture we just heard. It has an Euler product over geodesics rather than primes, but its zeros are known to be on the critical line, the non-trivial zeros, and they are these numbers. Now, the theorem of Dieter-Meyer expresses this thing as the determinant, Fredholm determinant, of a certain operator, 1 minus Ls, well, it's actually Ls squared, the way I'm about to define Ls. And Ls is a certain operator which is of trace class, so this determinant makes sense, Fredholm determinant. And I can even tell you what Ls is. You take the disk of radius 3/2 around the point, radius 3/2 around the point 2, so it includes the point 1, and you consider, I'll just put h of d for functions which are holomorphic on d, more specifically holomorphic on the interior, continuous on the boundary. And on this, I have a certain linear operator, Ls, and Ls simply sends psi of z, which is a holomorphic function in this disk, to a new holomorphic function. Don't worry about convergence, it's a trivial matter, so I'll just write it as if it converged, which it does if real part of S is bigger than a half. Exactly the values I don't care about, of course. It's the so-called transfer operator. I'm not going to go into where it comes from. It's the sum n from 0 to infinity, 1 over n plus z to the 2s, times psi of 1 plus 1 over n plus z. So that's an explicit operator. You can check easily that in the region of convergence, and it's easy to continue in S, that it's holomorphic. It's a new function in h of d, so it's an operator. It's of trace class, and its determinant of 1 minus Ls squared is this zeta function. Now, on the other hand, what Lewis did is something completely different. Lewis associated to f of z some function psi of z, which is a holomorphic function on the complex plane minus the real axis. So you cut the plane starting from 0 to the left, the usual place where you cut to be able to find a log, and he defines a certain holomorphic function which satisfies the Lewis functional equation. Well, I'll write it in the simpler form. Then you have to distinguish even and odd. There's also some business about even and odd mass forms, plus or minus z to the minus 2s, psi of 1 plus 1 over z. Now, so what Lewis claims, so this is Lewis, he claims that to each mass waveform you have a holomorphic function. F wasn't holomorphic. You have a holomorphic function satisfying this very strange relationship, holomorphic in the whole cut plane, and what's more, and some very mild growth assumption at 0. And then, conversely, if you have such a function, well, actually, we proved that, then you have a mass waveform. So the existence of a holomorphic solution of this very simple three-term function equation is another version of the existence of spectral parameter. Well, what does this have to do with Meyer's result and with what I'm talking about? I seem to have strayed completely. But notice that formally, if z gamma of S is 0, then Ls squared has the eigenvalue 1, because the determinant of 1 minus Ls squared becomes 0. So there exists a psi such that Ls squared of psi is psi, and so if I diagonalize, there exists a solution of Ls psi equals plus or minus psi, if and only if. But now if you look at this equation, so on the left we have plus or minus psi of z, because it's equal. On the right, the first term is 1 over z to the 2s, psi of 1 plus 1 over z. And all the other terms are exactly what they were before, but n, instead of going from 0 to infinity, now goes from 1 to infinity. I mean, sorry, if I subtract n equals 0, I write it separately. The other terms, n goes from 1 to infinity, but then n plus z is the same as z plus 1 plus a new n going from 0 to infinity. So it's simply the same expression with z replaced by z plus 1. So therefore, it's plus or minus psi of z plus 1. If you compare these, you see that they're identical. So in two totally different ways, you find that this amazing functional equation comes either from the interpretation of the Selberg zeta function as a Fredholm determinant, or by some rather complicated analytic procedure. This involved a series of integral transforms, Hankel transforms, and so on, to get from here to here. So this is a beautiful discovery about automorphic forms and how they fit into other pictures. And this has a cohomological interpretation, which I can't go into. It's a very interesting story that Lewis and I have been working out for years after his discovery. But let me say very briefly, sorry, is there a question, Dennis? It's a somewhat confusing story. But I wanted now to say, why is this an example of what I'm talking about? Well, the reason is this, so why is it on this list example 2? If I define f tilde of z in the following way, I take this Fourier expansion, which was non-holomorphic, with the Bessel functions. And now I make a new expansion, but I simply decree that it's holomorphic. So I simply take the sum an e to the 2 pi I n z. Well, there's obviously a problem with that. Since an can be positive or negative, of course, this won't converge. And so here I take n simply from 1 to infinity, and it turns out you need a normalizing factor n to the s minus a half. And then to use the other coefficients, I can't just ignore them. I put n to the s minus a half, a minus n, e to the minus 2 pi I n z, if z is in the lower half plane. So what I have now is a holomorphic function which is defined in two disjoint half planes, the upper half plane and the lower half plane. There's no connection between these functions. But what we showed is that if you take, well, f tilde of z is of course periodic because I made it that way. But if you try the other generator of SL2Z, then this f tilde is not modular, but it's nearly modular of weight, so to speak, 2s. And the difference is exactly this psi of z. And the point is that f, by definition, f tilde is by definition holomorphic in the upper and lower half plane. Therefore, if I take this as the definition of psi, it's also holomorphic in the upper and lower half plane. But the miracle is that if and only if the number s is an eigenvalue, the numbers a are the correct eigenfunctions, only in that case will this difference extend holomorphically across the positive real axis, and you'll get a function here. So that explains a certain connection, but I still haven't explained why it's an example. What about the rational numbers? Well, that's, after all this preparation, at least very short to say. Namely, it's a fact that this f tilde, which I defined in a completely arbitrary looking way by independent formulas in the upper and the lower half plane, they look completely separate. But if I take a rational number, then it's a theorem that the two limits of f from above and below agree. So this is a very funny kind of a function. It's defined in the upper half plane and in the lower half plane and at all rational points. And it's sort of, you move through the real line. So if I simply define f tilde of alpha for alpha rational as the limit which I just told you exists and is independent of how you do it, epsilon goes to 0 from either above or below. So let's say from above, and I put plus or minus. Then the function f tilde is continuous, actually it's c infinity. As you come towards any rational points on any vertical line through a rational number, this function, which was holomorphic here and holomorphic here, now becomes c infinity on the vertical line. It's a very strange function, but through irrational points it has no meaning. So this new function is now a function which is intrinsically only defined on q. It has absolutely no meaning anywhere else on the real line. But that function captures, it's easy to see that if it were 0, my function was 0. So this captures everything. So we've encoded our function with a function on the imaginary line. And now if you take this function, and for alpha positive, let's say, you take alpha tilde of alpha minus, well, I don't know which way I put the signs now. Now that this makes sense, f tilde is a totally discontinuous function. If you graph it on the computer, it just jumps around, it does nothing. But if you take the difference, f tilde of alpha minus f tilde of minus 1 over alpha, now on the rationals, then this extends to a continuous function. So this is now, in fact, it's a c infinity function, even analytic almost everywhere on R. So there's a very, very strange behavior now where, and you can see this is kind of a Cossack relation, as I said, this actually is a cohomological story, but I can't go into that. Sorry? S? Well, what do you mean? There's only one S. S is the eigenvalue. It's like the weight of a modular form. Yeah, S is the S we're looking for, and F is the F with that eigenvalue. So S is the spectral parameter for my function. That's absolutely key here. No, otherwise, I mean, this can't be true for any two S's, because if you subtract, you find that F is identically 0. No, I mean, this is a functional equation, like the functional equation for delta, with where there S would be 6. Okay, so my time is nearly over, and I haven't yet said either of the two things I wanted to tell you. So let me at least pass quickly to examples 3 and 4. My time really almost over. It's hard to believe. Sorry? Aha. Oh, well. However, I think I'm now going to revert to normal speed. Everybody screams. Okay, let me give example 3, very brief, although it's the one that started me out on this. this was an example. Maxim Kontsevich, in a lecture in Bonn about 3 years ago, wrote down the following strange thing. Qn's, remember this is 1 minus q times 1 minus q squared up to 1 minus q to the n. And he just wrote down this very peculiar function. What's peculiar about it is that it doesn't converge anywhere. If q is bigger than 1, the terms go to infinity. And if q is less than 1 in absolute value, the terms tend to a limit, which is the Dedekind eta function. And so the infinite sum is still divergent because the terms have a non-zero limit. So this makes no sense. So it's nonsense if q is either bigger than 1 or less than 1. It's no good. And also, of course, if q is equal to 1, it's no good. It's even worse. It oscillates all around. It's completely crazy, unless, of course, q happens to be, let's say, psi, which is the root of unity, so e to the 2 pi I alpha for some rational number alpha. In that case, you don't even have to be Maxim to see that the nth term of this, as soon as n is big enough, will become 0. And so this series, which is trying very hard to diverge, is stymied by the fact that it terminates. So we have this function, which therefore makes perfectly good sense. So in this case, f of psi exists, and it's an element of z of psi. So it's a rather strange function. Well, I guess polynomials do the same, but it takes on values in a different number field every time you change the argument of the number of the function. Now, I studied this function, and I found two nice things about it, one of which is simply nice, and one of which led to the story that I've been telling today. So one of the things, you see, this does make sense. Not only it makes sense at rational numbers, but it makes sense to infinite order. If you go towards, for instance, a fifth root of unity, then as soon as n is bigger than 5, this product is 0. But as soon as n is bigger than 10, it vanishes doubly. After 15, it vanishes triply. So to any order, you can compute this around any root of unity. So this function actually exists. It's kind of little hairs, like we saw in the mandrel. At every rational point, there's a little hair coming out, and you can see just an infinitesimal expansion, the whole Taylor expansion at that point. So it has Taylor expansions at all rational points, but they have absolutely nothing to do with each other. I mean, in that direction, only this way. Well, if you do that, the obvious thing to do first is take q to be 1 minus epsilon. So then we write f of 1 minus epsilon. Well, then the nth term is divisible by epsilon to the n. So if you just start computing, then you quickly find some coefficients. I'll write down the first few. Well, I don't have to write them all down, do I? Okay. So you find some expansion, and then what you do, of course, in this modern day and age, you type it into the internet, into Sloan's Handbook of Integer Sequences, which is now automated, and you ask whether anybody's ever seen this sequence of numbers before, 1, 1, 2, 5, 15, 53, 2, 17. Well, usually when you do this, it doesn't work, or if it does, it's so easy that you feel embarrassed that you asked. But this time it was very good, because the answer was yes. A person that I didn't at that time yet know. He was a graduate student, Bulgarian graduate student in Berlin. This is about a year ago. He's now got his degree. Stoimanov had just found these functions, the same sequence of numbers a few months earlier, less than half a year earlier, and had put them on the internet with a totally different definition. And his definition, so if the nth coefficient is called Cn, then at least the table, which agreed for the first 30 numbers, was the number of regularized, this is his definition, regularized linear chord diagrams, which is a combinatorial object. I was going to define it completely, but I'll just tell you what it is. If you know what chord diagrams are, they're the things you count when you count Vasiliev invariants. And I won't define regularized unless somebody asks, but I could write a little picture of the first few. For instance, if n is 3, well, I'll do it even easier case. If n is 2, then there are 3 possible chord diagrams. The chord diagram is just a diagram of chords, of n chords, and here there are 2, and this is regular, and this is regular, and this isn't. Okay, so there's a definition. It's very, very simple to say. And the point is that you count these chord diagrams because the set of chord diagrams of the vector space they generate, modulo certain equivalence relation, is the vector space of Vasiliev invariants of knots, whose dimension people are very interested in computing. So the number of all chord diagrams is an upper bound, but it's a very bad one. But he showed that each equivalence class contained at least one regularized representative. Therefore, the number of these is an upper bound, and it's far better than previously known upper bounds. And he had made a crude estimate of Cn using his algorithmic description of Cn. But it turned out to really be a theorem that these Cn's are the same as these coefficients, and using that you could give exact asymptotics. So that's an amusing application to a problem of combinatorial knot theory. But it turned out that wasn't really the right way to do it, and the right way to do it, from the point of view of the essence of the function, rather than those particular coefficients, was not to write q as 1 minus epsilon, but as you might expect, to write it as e to the minus epsilon, corresponding to e to the 2 pi iz, with c as 2 pi I epsilon or something. And again, it's better to multiply, so let me just call it q. It's better to multiply by 1 minus q to the 1/24th as usual, because you can see that the terms are tended to the Dedekind eta function. And if you do that, then you find something very pretty. First of all, you find the following expansion, Tn over n factorial times t over 24 to the n, where the t zeros are certain numbers, obviously. And these numbers, again, you can look up. Actually, I didn't have to because I recognized them by myself, but then I did look them up to find out who had written them down first. And they're called the Glaisher T numbers. And they were defined in 1898 by Glaisher. And what these numbers are, well, there are two ways of defining them. One is, if you make a slightly different generating function with exactly the same Tn's, but instead of divided by n factorial, you divide by 2n plus 1 factorial, then it's an elementary function. It's sine x over 1 minus 4 sine squared x. So that defines them and defines everything. But a better definition is that Tn up to some renormalization is the L series, as we've been hearing about in the previous, I guess, both lectures. It's the L series of that very same character 12 over dot, which I already wrote down in connection with the Dedekind eta function at negative integer values. So these are special values of L series, something that number theorists study a lot. But this is still not the real story. The real story is that this thing is really equal, in some very bizarre sense, to minus a half times the sum n times that same 12 over n times q to the n squared over 24. In other words, you take the same expansion we had for the Dedekind eta function, you multiply the nth term by n. So this is very strange. It means that the original f without the q is minus a half plus 5 halves q plus 7 halves q squared minus 11 halves q to the 5th, and so on. It looks completely crazy since nothing was half integral in these coefficients. But of course, this didn't converge anyway as a power series in q. What this means is that the limiting value of this, which is nearly a modular form, it's an integral of a modular form, the limiting value of this at any root of unity agrees with the value of this at any root of unity, and they agree to infinite order. Okay, so that was example 3, and now I've some very short negative time to tell you what example 4, the main one, would have been about. So just in 2 words, if you have hyperbolic 3 manifolds, not hyperbolic, 3 manifolds, then you can associate to them certain quantum invariants. This was done by a not very rigorous method, or not at all rigorous, by Witten, and then a rigorous definition, which is meant to capture the same contents, was given by Reshetykhin and Turaev. These are famous invariants. There are many variants of them. And in certain extremely special cases, you can compute these things. And what these invariants are, so it's a certain function depending on m, but it's a function, again, which is really only defined at roots of unity. I mean, Witten's definition should be defined everywhere, but it makes no sense. And the Reshetykhin Turaev invariant only makes sense at roots of unity. Now, for certain very special manifolds, various people, in particular Ruth Lawrence and Lev Rozansky, have given explicit formulas how to compute these, but only for extremely special manifolds, torus knots, Seifert fibrations, and so on. And by looking at one of those, it's actually Joseph Bernstein suggested that that might happen, and it really did. If we took the case of the Poincare sphere, the icosahedral sphere, very famous 3-manifold, then one could compute those things explicitly. They looked very like the things coming from this kind of peculiar nearly modular form expansion, and it turned out that they really were. So the same kind of strange formula which is true here, that you kind of half integrate a theta series, exactly the same thing happened here, and so I'll just end with that. I had all the formulas prepared, but I have to leave them out, that at least in the one case, well, we have now families of cases, but only very special, so we don't know how general it is. But at least for certain manifolds, these quantum invariants, which are intrinsically defined, well-defined at roots of unity, are exactly the same as these strange numbers coming from modular forms or Mach modular forms. And in fact, in that particular case, it's related to both a Mach theta function, again, I didn't get to it, and a true modular function. So there is this connection between topology, combinatorics, and modular forms, as promised, all using Q. So thank you.